If you are applying strict object-oriented programming, then this case which I will show today must have happened to you many times already. There is one annoying thing an object can never do, no matter what you tried. Watch carefully. At some point through the demo, you will start thinking, hey, I have been here already, and I have failed every single time. I will explain why you have failed and what you could try instead. As it happens, the answer will lie in object-oriented design. This is the demo application modeling a bookstore, and the feature we will discuss today is this page. It is showing invoices. The color is indicating the state of the invoice. Green ones are paid, the others are not paid. It is not only about the color, the styling, but also about behavior. The unpaid invoices have this button where we can mark them as paid. Now, this is the source code where these invoices and all the operations on them have been implemented. There are many types, there are also many requirements related to invoices, as you can imagine. Instead of working with that original source code, I will give you a stripped down variant, and I will implement two solutions, the object-oriented one and the functional one, so that you can see where the problem is and how we can address it. So, one implementation will follow the principles of object-oriented programming, I will put it here, and the other one will follow the principles of functional programming, that will be in this file here, and you will be able to see the difference in the critical capability. I will start from the object-oriented solution that will outline the principal problem, which again, an object-oriented, a pure object-oriented design cannot solve. There will be the class for the invoice. It could be the interface, but I need some state, and that's why I'm using the base class. But what about the payment? Will it be a nullable property here? Well, that would ruin my object-oriented design. We don't want to create classes that are doing more than one thing. A more natural approach is to turn this class abstract and then derive one class to model outstanding invoices. Those are the invoices that don't have a date of payment. And another model would model the paid invoices, and you can see that these invoices will have a date-only property which indicates when the invoice was paid, and that property would not be nullable, of course. Now, any processing, any behavior, even displaying of these invoices can be made polymorphic. We can follow the principles of object-oriented design through the entire application when invoices are done this way. For example, the outstanding invoices would have that paid button in the UI, and they would expose an operation to mark as paid. But the problem is, I don't know what to do in this operation. Now you already begin to see that we do have a problem here. In a more engaged case, all invoices could support setting the payment date. And now I know what to do with the paid invoice. Just update the property. That would require this class to be mutable to support mutating the paid date. But that is not a problem. We're accustomed to having mutable classes in an object-oriented design. So everything is still perfectly fine with object-oriented design. But again, I have no clue how to implement that same operation in the outstanding invoice. Now, this is a well-known problem in object-oriented programming. And that is the problem we will try to address in this video. The problem, in essence, is that making this outstanding invoice paid means to change its runtime type. And that is the one thing an object can never do in object-oriented programming. It cannot change its runtime type during its lifetime. A common solution is to return the polymorphic object. Now, this already begins to look like the state design pattern, doesn't it? Well, yes. This is the state design pattern which I will essentially implement now, but that will also have its own downsides. Let's see. The implementation suddenly becomes straightforward. Just instantiate the new paid invoice and return it, and that will effectively introduce an object with a different runtime type. That is exactly what we couldn't do inside this object. The paid invoice will get away with just returning the mutated this. This is not really a clean design, but again, if we are following the principles of object-oriented programming, this is an everyday case. We do this all the time. But now, after implementing this design and apparently getting away from the problem, solving the problem here in these classes, we have opened a totally different set of problems we didn't have before. Imagine that this application, and that is actually true, is using an ORM. ORM, Object-Relational Mappers. They are tracking the objects they gave you from the database so that you can mutate them, and the ORM will capture the changes and produce SQL statements that will do the changes in persistence. But what if the outstanding invoice here returned a new object, as it did? The ORM will have no clue that that object exists, and that it is a new version of that object it is tracking already. So we have just broken the ORM. We can solve that by treating this operation as a special case and telling, hey, you're tracking this object now. This is the new version, okay, so try to do something with that database. But that is not what ORMs were imagined to do. On a related note, you might be worried about breaking the command query separation principle on paid invoices. We can also return a new instance here. That would still be the paid invoice object, but a different one. And again, we are confusing the ORM once more. Either way, there is something off with object-oriented design when it comes to this kind of problems. The state design pattern is addressing this kind of issues, and it's not doing that in an entirely satisfactory way. I'm sorry. There is no absolute solution to this problem within the premises of object-oriented programming. I will now show you the same design in functional programming style, and you will see that we won't even have this problem. Before that, let me ask you a favor. If you liked this video so far, please press the like button. That will help me spread the word about this video. Thank you very much. And if you want to see the source code, there's a lot of code in this demo. The source code is available to sponsors of this channel. Become the sponsor, follow the link in the description, that is the link to my Patreon page. By becoming the sponsor, you will not only help me maintain this channel, but also have access to source code of this demo and all other demos that are shown in this channel. Thank you very much. Let's get to some functional programming now. In a functional model, we create types, not classes. An abstract record will serve as the base invoice. A derived record will model outstanding invoices, and another derived record will add the payment date, and it will model the paid invoices. This completes the type modeling stage, the first stage in designing a functional model. Now we step to modeling behavior. Normally, behavior on functional types is defined in extension methods applied to the hierarchy of types. In functional programming, we would transform every value and instance of a type into a new value. it's not allowed to mutate an existing value. This extension method applied to an abstract invoice will always return a new invoice instance. So we don't even have that question we had with object-oriented classes. What do we do with an outstanding invoice? Well, nothing, turn it into something else, always. Now to implementation, a functional kind of a function is almost invariably designed in form of a pattern matching expression. If the invoice is the outstanding one, then create a new paid invoice with specified date. If the incoming invoice is paid, then use non-destructive mutation to update the date. That will create a new instance of that same type. And then comes the dirty part. We must plug the switch expression with catch-all pattern. This is the deficiency of C# at this moment. I hope that soon enough we will have a proper pattern matching construct that can check whether we have covered all the existing types. That will require support for discriminated unions, another complicated concept from functional programming. If you want to learn more about discriminated unions, especially in C#, there is the video above that you can watch later and learn more about using, for example, records in this mode in C#. If you look at this code, this is doing everything that object-oriented model was doing, and it is shorter by at least a factor of 2. That is quite common. When you do functional modeling and functional programming, even in C#, which is not exactly suitable for that, your code will be cut to at least a half, if not more. But then compare this solution and that one. In functional programming, in a functional model, you are assuming that values will change their runtime type as they progress through the functions. It is a given. It will always happen. And so you do expect that if you are using an ORM in an application like this one, then the entire application will already be organized around the idea that the ORM is just serving you the objects populated from the database, but before you update the database, you must say these are the original objects, these are the new objects, now find the differences and create the statements for me. That is an everyday event in functional programming. Nobody will be confused by what happened here. So I have given you something to think about, haven't I? This is an interesting topic, but also an important one, because if you observe how the C# programming language is changing, and has been changing in the recent couple of years, you will see that it is going in this direction. So start thinking about this now. Try functional programming with C#, try functional design with records and extension methods. That will give you a few options that you didn't have with object-oriented models. And see you in the next episode.